Okay, let's start. So it's a new section called Section 8. Section 8 on causal systems. Section 8. So a system S is causal when the response of the system to X is such that at any instant n naught, y of n naught does not depend on the future of x of n. That means does not depend on x of n naught plus 1, x of n naught plus 2, etc. You come here. Punishment. So that's the definition of causal is that you want the output not to depend on the future of the input. Okay, this is the future of the input. X of n naught. Okay, to make it to emphasize this is x of n naught plus 3. All right. So causal. It's not casual. This morning, one got shot because he said casual. So let's do some exercise. Example 1. Consider the system that performs time reversal. Is it causal or is it not causal? You think about this and then you vote. How many of you vote this is causal? How many of you vote this is not causal? So, for example, what is x tilde of minus 1? So if you call this n naught, then this will be what? N naught plus 2, future, not causal. Example 3. I need to go back to kindergarten. What is S of what is the causality? Is it causal or not? So this is my favorite system that I introduced to you from the very beginning. Okay, how many of you vote this is causal? How many of you vote this is not causal? Okay, so this is y of n. What is y of minus 1? So this is, if you call this a naught, then what is this? Not causal. So far you still win, but not by much. How many of you vote this is causal? You see, you too? Okay. How many of you vote this is not causal? The voting participation is so low. Doesn't sound good. Huh? Are you sure? Yes, it's causal. So since nobody disagrees, then I move on. So please vote so that I know. So so this is y of n, okay? So does y of n not depend on x of n naught plus 1, x of n naught plus 2? No, it does not. Done. You got tricked because of the n plus 1, but this is not about x. This you can calculate any time you want. It doesn't depend on the input. Such that y of n is the sum when k goes from minus infinity. Okay, this is the sum of x of k plus 2. Okay, let's vote. How many of you vote this is causal? How many of you vote this is not causal? Yeah, you did vote. So what is y of n naught? Okay, what is y of n? Okay, so you have a sum, right? So I'm going to write it starting from k from the top, and I'm going to add up all the terms from the top to the bottom, okay? Because I cannot start from minus infinity, so I start from the top. So when k is, the top is k equals n minus 3, so you get what? X of n minus 3 plus 2. And the next is what? X of n minus 4 plus 2. Yeah, because I'm going down now. Because it's the top. I'm starting from the top. Etc., right? Yeah. So this is how much? So y over naught is what? I tricked you because you got tricked because there's a plus 2 here. Yeah, but it's not a problem because I'm stopping the sum before I reach n. Here it was just a trap. Okay, now here I have given you any system. Any system can be causal or not causal. Now, an LTI system can also be causal or not causal, right? Because LTI and causality are independent properties. However, when a system is LTI, you know that you know the system completely as soon as you know the impulse response. Right? So the impulse response characterizes your system completely. So it looks like logically, to decide whether the system is causal or not, you should be able to see it just by inspecting the impulse response. Because the impulse response contains every information about the system, so it is expected that you'll be able to determine causality just by looking at the impulse response. I'm not telling you how yet, but it seems that it should be possible. And the answer is it's possible, and it's a theorem. Do you like theorems? And you know I like to give names to properties like time shift 1, time shift 2, things like that. So this theorem I give a name so that we know what theorem to refer to, and this one is called helicopter 1. You know, like time shift 1, time shift 2, helicopter 1, helicopter 2. You know what is a helicopter, right? You have prerequisite? All right, so let S be LTI, and let G of n be its impulse response. Then the theorem says the following: S is causal if and only if, you understand, if and only if G of n equals 0 for all n negative. Does it remind you of something? It reminds you of the job interview of last time. Remember what happened? When as soon as you put something non-zero for negative n, we could not implement the system as soon as there was an impulse on the negative side. So this theorem actually tells you that this is really a necessary and sufficient condition for the system to be causal when S is LTI. So you want to know why. Oh, I have a question. Is there any other class in EE that gives proofs? Yeah, which one? Yes, they have proofs. What proof? It's a proof. So there are proofs. Electromagnetics also has proofs. Fiber optics. What?
There's only one power.
Sorry, I didn't hear.
There's only one power.
Proof. So, since this S is LTI, since S is LTI, we know by theorem, we know by theorem 1 that if you look at the output of the system, then it is equal to G of n. So I can write it this way, but it will be more convenient to write it like that, using commutativity, because then this implies that for each n, then y of n. Actually, I can write directly with y naught, n naught. Y of n naught is the sum of g of k x of n naught minus k. All right, so far we use what we know about LTI system. Now, if and only if means two implications. We are going to prove each of them separately, but I'm going to start with the easy one. The easy proof is going like that. So assume that, so we assume this is true. And then prove that S is causal. Okay? Now, we know that we have this we know that we have this expansion. Okay? But we assume that G of n is 0 for n negative. So is it necessary to perform this summation from minus infinity to plus infinity? No? So how can I limit this? So we do have this. But if you write this extensively, what do you get? At k equals 0, you get then next Can we conclude? We can already conclude. S is it depends on the present and the past. So it's causal. Wow. Okay, so now we are going to assume the other one. Assume S is causal and prove this, but it will be easier to prove the contrapositive. We can also we can equivalently prove the contrapositive. Yeah, but you have to tell me what that means. Yeah. Yeah. Yes. You are supposed to know. Yeah, because it's in logic. It's in logic.
But here they don't teach theorem, like a theorem in logic, only based on that.
No, in general. Okay.
Well, we never take a class on the only computation. Mathematical proof.
All right. You must know that A implies B is the same thing as not B implies not A. You know that?
I know that from mathematical proof.
Fine. But usually you know. Students, they know that. So this one is the contrapositive of this. So saying this or saying that is the same thing. I can give you an example. When it rains, John stays inside. When it rains, John stays inside. So that means it rains implies John stays inside. What is the contrapositive? When John is outside, then it does not rain. It's saying exactly the same thing. You get that? Now, what is the contrapositive of this implies this? It's not this implies not this. All right? So prove that not this implies as not causal. All right, so we can prove this and it will be the same. However, students have hard time telling me what is not this. Students have hard time telling me logically what this means, not this. Can you rephrase this in a more explicit way? Okay, let me write down. G of n not 0. You don't agree?
Huh? No, I mean, I know.
All right, so you tell me, you propose something different.
Yes, it's
Okay. G of n equal to 0. if you have a different suggestion, please let me, please. Same, any or all. Okay, we have enough to choose from, okay? Lots of choice. Let's vote. Let's vote. Okay, how many of you vote for the first one? Wait, somebody has to vote for himself. How many of you vote for the second one? How many vote for the third one? How many vote for the last one? It's not so clear. It's very disappointing because I think you do it mechanically. You do it mechanically, you don't do it by logic. Because now I'm going to rephrase this in like John going out when it rains. And then this, when I say in this way, you can get the right answer. Because if I do that, you don't do it mechanically, you do it by logic. But here, somehow you just do it mechanically and you cannot get the right answer. I'm not telling you which one is the right answer, but obviously many of you are wrong because, okay? So I'm going to say something that is more concrete. It's a statement, and then you have to tell me what is not that statement. My statement is to claim that all students on my left side have a black notebook. All students on my left side have a black notebook. Can you tell me what is not this? There is the not this is there is at least one student on my left side that does not have a black notebook. Isn't that obvious? All right. Now this is black notebook, this is left side. So there's at least one student on the left side that does not have a black notebook. It's this one. You see, this is strange, is that once you see mathematical symbols, you just do it mechanically. But if I do it with common sense, you can find it. In fact, this way of proceeding is not just for this. It's even for equations, you should do it also with physical real sense, not mechanically. All right. So the correct answer is this one. All right. And if you still don't understand, you convert that into black notebook and left side, and then you will get it. Actually, I'm not supposed to teach that. This is not a class of logic, but so this is the same thing as this. So assume this. All right. So we assume this. So we are going to say, let's say, call it N1. So maybe I can rephrase this. For some N1, so G of N1 is not zero for some N1, negative. All right. So let's go back to that expansion that is always true. Now, among these terms, one of them is g of n1 x of n0 minus n1. Do you agree with this? Because k goes from minus infinity to plus infinity, so among them you are going to have this term. Do you agree? Now, by assumption, this is non-zero. Therefore, y of n0 depends on x of n0 minus n1. You agree? All right. Is that future or past? Yes. Yes, this is the future, but this morning they just couldn't believe me. And then they realized, and then I showed them something brilliant. Isn't that brilliant? That was not easy to see, eh? So this is future. So S is not causal. We assume this. We assume this because we assume the contrapositive. We assume not this. I'm done with the proof. So what have I done? I have proved that these two properties are equivalent, but in a different way. Instead of proving this implies this and this implies that, another way to do that is to show this implies, what we did is that we showed that this implies this, and not this implies not that. That is sufficient to prove the equivalence. Okay. All right. Next question. Why did I call this helicopter one? Okay. The reason is not easy to explain in this room because there's no window. I used to teach that in a room upstairs, a Mac building with a window. But imagine that after the class you return home. You have to take the subway. It will take you 1 hour and a half. Yeah. But imagine that at that moment when you return home, there's a helicopter that presents itself at the window, and there's a guy, the pilot say, hey, come, I can fly you back home in 5 minutes, within 5 minutes. Will you reject it? Let me tell you, I will jump in it. You know, this morning they said, yeah, no, I don't want to take it. But then when it comes to doing something at the exam, and then you have two methods. You have a helicopter method, and then you have like the turtle method. Which one do you prefer? Yeah, you see, yeah? So why am I saying this? When I ask you, is the system causal, if the system has no particular property, there's no choice. You have to go back to the original definition. But if I happen to give you a system that is LTI, and you know the impulse response, you don't have to go through the original causality definition. You just inspect the impulse response, and you just look at if there is anything on the negative side, and right away you can say yes or no. The theorem says it.
Wait, I think you said not all LTIs are causal.
What?
You said not all LTIs are causal.
But what I'm saying is that you have a criterion to know in one shot if it's causal or not. Because there's the IFF. Yeah. So I had to invent this word, this term helicopter, to make it attractive because students wouldn't do it. But the problem is that at some point it became so attractive that students would take the helicopter when there is none. It's a big problem when the classroom is upstairs. And so now a typical mistake is that I see at the exam, students say, according to helicopter 1, this is causal. Boom. But the system is not LTI. So you know what I write in red? I write, you jumped out of a window without helicopter behind. And then I write, it hurts. But it's not finished. Next to it, I write 0. But what is funny is that I'm saying that to you. And for sure, quite a lot of you are going to take helicopter when there is none. All right. Now, if there's a helicopter and you don't take it, I don't penalize you. You penalize yourself because you're going to lose time in deriving things. All right. So now I can move on to the next paragraph, which is the last section of chapter 1. No, I mean, it's simple. I give you a system. If it's LTI, you can do it. And if it's not LTI, you can...
So we give you different step. Either it can be, I mean, you give me one system. If it's LTI, causal. Not LTI, not causal.
No. You are mistaking it. No.
Exactly.
No, read this. If it's LTI, then this is equivalent to this. So that means when it's LTI, you don't have to go back to the original definition to answer the question if it's causal or not. You just look at the impulse response. Just look at this. Just look at this. Just see if this is true. That's it. I mean, this is all it says, right? Okay. All right. Now the last paragraph of this chapter 1, it was a long chapter, wasn't it? Was it? Stable systems. It's the hardest, so there will be 4 properties to know, and this one is the hardest among all. One difficulty is that to understand what is a stable system, you need to first learn what is a bounded sequence. So there's a prerequisite, preliminaries. You want to learn about the notion of bounded sequence. So a sequence x of n is bounded. When there exists a constant A, positive, such that for all, that's very important, for all n, x of n in absolute value is less than A. That's the definition of a bounded sequence. Now, if if x of n is real, then you know that x of n less than a, it means the same thing as x of n between a and minus a. So the fact that it's bounded is something that you can visualize. Because if you plot the sequence, x of n, when it's bounded, you can see that when you plot the successive amplitudes, they will have to have a ceiling. It cannot go beyond plus a, and it cannot go below minus a. In fact, I'm going to use a different line type. So graphically, there will be a ceiling and a floor throughout the whole axis. Okay, so it's bounded is something visual. So now we go through fun. Example 1. Ready to vote? Is that the question? If it's complex, is that the question? You have a picture, but I cannot put it in on the paper because complex you have 2 values. So you could look at this in a tube. In a real tube, you have a tube, so it should fit inside. Sorry, I cannot explain more. This is only valid when x of n is real. If it's complex, then it's more complicated because you have the real part and the imaginary part. All right, ready to vote? Who votes that this is bounded? You're not afraid to be minority? Bounded? Ah. Bounded? 3, 4? Okay, you're not alone. Anybody wants to join? How many of you vote this is not bounded? Okay. Things are simple. If it's bounded, that means you should be able to give me a value of a. Constant, okay? You should be able to give me a number like 2, 3. No, it has to be a constant. Or you should be able, when you plot it, you should be able to put a cap, a ceiling, and a floor. Now, if you plot this, what does it look like? Yes, it's a ramp. It's not bounded, obviously. Today the front row is very talkative. Vote. How many of you vote this is bounded? How many of you vote this is not bounded? Anybody changing his mind? Her mind? All right, so do you know what is the limit of x of n when n goes to infinity? Limit, yeah. When n goes to infinity. When n goes to plus infinity, where does it end? Where does it go? You cannot answer. This is basic calculus.
Yeah, you have to pass over the end and then when you finish, you can't do anything.
Yes. Ah, you have been a bit slow. What about n going to minus infinity? All right, all right, all right. So the reasoning is that when n is far enough, it looks like it's going to be bounded, right? Because it has to go to tend to 1, right? So we don't know how fast it goes to 1, but at some point it will be close enough, so such that when you are far enough away, it's going to be bounded after a while. But the problem is that in between, how do you know the signal is bounded in between?
I mean, let's say that you give us, if you give us a equals to 0.5, it will not work. It will not be bounded, right?
We want to prove that there exists a constant. Exists.
Oh.
Exists.
So but a is a constant, correct?
Constant, it has to be everywhere. It has to be the same value everywhere.
Okay, so a is equal to 0.5. Will it still be bounded?
Wait. You want to find A before the existence of A, before you know if it's bounded or not. I think you are the process of finding A is going to be part of the answer whether it's bounded or not. It's finding A.
Oh, finding it, okay. But if a is given,
We don't. It's not given.
okay.
It's not given. It exists. It exists. Sometimes you don't even know the value, but you know it exists.
Okay.
But I return to my reasoning. When you go far away, you know you are going to be. I'm not giving numbers, but it's intuitive. If n is large enough, you know it's going to be bounded, right? But the problem is that in between, how do you know it's going to be bounded in between? That's the issue.
But here it seems like the top is wrong and the bottom is also wrong. So it's always going to be
In between what?
in between some numbers.
In between some numbers. Which ones?
I mean, a lot of numbers, we don't know exactly, but we know it's going to be between whatever the hint is constant.
I'm pushing that question because there's an answer to this question. Okay. There is something I'm going to claim, even though I don't know what is the solution. But I'm going to say something, and you tell me if what I'm saying is true or not. You are shorter than the tallest man on earth. Is that true? But where is it? Where is he? We don't know. But he exists. He exists, right? So, when I'm saying when you are far away enough, we don't have problems. That means when we are not far away enough, that means you are between two numbers that are some numbers, right? Let's say maybe beyond 1 million we are fine, but before 1 million we still don't know. So you are between minus 1 million and plus 1 million. Let me tell you is that all of these numbers are smaller than the largest man, if you like, among these 2 million numbers. Why? So what is helping solving this question is that if you have a finite number of numbers, one of them is the biggest. That's the answer. Done. So this is bounded. Was that difficult?
So I couldn't apply to what it was before, because before it was always growing. So you couldn't say that simple. Yeah, but before it was.
Before actually the limit was infinite.
Yeah.
All right. Example 3 is the last example, but don't worry. Here I'm putting this example for me to have fun only. That means you're not going to understand it, but it's fine. It's for me to just have fun. Because I want to win. So whoever wants to have fun with me, please join. Okay, I'm going to give you some hints. Can cosine of n be equal to 0?
No, 1/0 makes it constant.
Oh, no.
No, I'm asking, can cosine of n be equal to 0?
Yes.
Yes.
With what value of n?
Five.
So I'm going to shoot you. Why?
Yeah, it is only take
Yes, n is only integers.
because
It's Isabel! Okay, I stop. I'm asking again the question. Can cosine of n be equal to 0?
You're gonna get shot.
Cosine of x is 0 when x is pi over 2 modulo pi, right? These are irrational numbers. No integer can be an irrational number. All right? So cosine of n is never 0. Therefore, this sequence is well defined. Okay? So I just wanted to give you some preparation before you vote. Ready to vote? Okay, let's vote. How many of you vote this is bounded? Okay, vote now. How many of you vote this is bounded? How many of you vote this is not bounded? Okay, so those of you who said it's not bounded, what's the idea behind this answer? No, but because you voted it's bounded. Yeah, but I'm asking the question for those who voted not bounded. I want to hear their reasoning.
Yeah, as n goes to infinity, 1/cosine n, that actually gets smaller and smaller. So if
How do you know that? No, but
it's the 1/that value.
I mean cosine, 1/cosine becomes, are you talking about cosine or 1/cosine?
1/cosine.
All right, so it looks like it's going to be bounded according to you.
Cosine of n was extended, so we're not taking it away.
Right, so 1/cosine you say becomes smaller, so it looks like it's going to be bounded. You are saying that 1/cosine it becomes smaller.
Yeah, but it never touches 0. It gets closer.
Yeah, right, yeah.
You want to change your vote?
No, it's okay.
So you're reasoning that, okay, for those who replied not bounded, I want to hear what is your idea behind this. It looks like it's very unclear. Let's vote again. How many of you vote this is not bounded? So you persist, it's only 2, okay. All right, so now you explain to me why you say that. Because you are saying that 1 over cosine is getting smaller and smaller, and now you say it's not bounded.
It's always changing. It's not like to be bounded has to have a existing constant, right? It never gives you like one like constant value, like one range or one limit. It keeps changing. So I don't know. I'm not a team.
Cosine of n is never 0, so never 0.
As an inverted parabola, right? You start from the very base value, and then you take negative n divided by n, because cosine goes up and down, so it has negative n positive on same value, so it goes inverted parabola, and then hyperbolic.
Okay, I don't understand.
Professor, I want to change my vote to bounded. Did you hear it?
No, but no, but I already changed. Okay, so okay, so 13. Right. Yeah, okay.
It's not bounded.
Can you please explain? I just couldn't explain, but.
Okay, I told you, I gave this example just for fun for me. All right, so you will never understand it. Yes. It means that to understand this, you need to take a graduate course in Department of Mathematics. So in Department of Mathematics, PhD level course.
Can you just illustrate?
Maybe I can tell you after the class, but I just wanted to have a bit of fun. You see. So you don't have to worry, no question like that at the exam. Yeah. I don't know. I don't know. No, I understand, but I'm not sure because I'm not good enough in math to be able to. Maybe my colleague would say right away, yes, you are right or not. Yeah, I'm not sure about this. No, I'm not sure. But you see, the answer is that we don't have to worry about this because we know that without looking at things explicitly, there's some reason that it's going to be bounded. All right, so now I want to go into stable systems because this is what we're interested in. Stable systems. Okay, let me tell you the property of stability. Students, this is where students, they get really confused for some reason. So I warn you in advance. The statement is going to be simple, but students, they misunderstand it. A system S is stable when for any input x of n that is bounded, the response y of n is also bounded. This is called the Bibo criterion. Bounded input implies that the output is bounded. So that's the property. A system is stable when having a bounded input automatically implies that the output is bounded. So where students, they get confused is that often they ask me, all right, but what if I input something not bounded? Then the answer is that, yeah, you can do it. It's a free country, but I don't care. I don't care. This has nothing to do with stability. Another type of question is that I get where students get completely confused is that, so do you mean that stability depends on what input you consider? No, this is wrong approach. Stability is not a property that depends on the input. It's a property of the system. But to check stability, you have to see its behavior for bounded inputs, because that's the definition of stability. Whatever your system does when their input is not bounded does not give any answer to stability. It's like when I ask you, is the system time invariant? Then you have to shift the input, right? You're not going to ask me, what if I scale the input? I will say you can do it, but I don't care because this has nothing to do with the time invariance. Same for stability. You want to input something not bounded, you can do it if you want, but this has nothing to do with stability. All right? So now we are going to have some fun. Example 1. All right, so the system is going to be stable or not. It's going to be yes or no. It's like linearity, it's like time invariance, it's like causality. It's going to be yes or no. This is actually what I like about this type of exercise. It's not like politics. In politics, there's no yes or no. Politics is like whatever you want. Ready to vote? Okay. How many of you vote yes? How many of you vote no, it's not stable? Wow. All right, so to prove the system is stable, you have to take any input that is bounded and then observe what happens. So take x of n bounded. That means what? It means that x of n is less than some constant a in absolute value. So you assume that your x of n is like that. Can you prove that y of n is going to be of that property?
Yes.
No, because you want to prove that it works for all possible bounded input. You have to assume you have to prove it for all possible bounded input. So you cannot take one specifically. You have to prove it for all of them. For all of them. So I'm going to do it now, okay? So take any input, any given input, x of n, that is bounded. So since we assume it's bounded, then there exists a constant a such that x of n is less than a for all n. This is what we assume, okay? Because we need to assume that. So now y of n is x of n squared minus 1. So what is going to be the absolute value of y of n? Is going to be the absolute value of x of n squared minus 1. But what do we know about x of n? We know that this is less than a for all n. So if it's true for all n, is it true for this one? Yeah. It's true for all n. So 0, 1, 2, 3, 4, 5, all the way to plus infinity and minus infinity. This is one of these numbers. So this must be less than a also. It's not that you don't need, it's that it is not allowed. It's not allowed to have a specific example because this is not proving anything. On the other hand, to show this is not stable, yes, you just need to provide one particular example. All right? So y of n is bounded. So y of n is bounded. Therefore, S is stable. Example 2. You understand the notation? Exponential? Okay. Ready to vote? Ready to vote? Okay, how many of you vote that this is stable? Okay, I need to put glasses like that to see who you are. Okay. All right, how many of you vote this is not stable? You are alone. Are you sure you don't want to change your mind? Are you sure? He's sure. He's really like... It goes like crazy, huh? Yeah, it goes like crazy. It goes like crazy, yes. So I'm going to prove it to you. All right, so we assume x of n is bounded, so there exists a such that x of n is less than a. You agree? Right. Okay, now what is y of n? So the first thing to notice is that this is always positive, all right? So that is, there's no issue about this, okay? But it could be large, that's the problem. But look, so this implies in particular that x of n is less than a. Because it's the upper bound, right? Yeah. Okay. Now, did you know that the exponential is an increasing function? This means that if x is less than a, then exponential of x of n is less than exponential of A? You agree with this?
Yes.
So this is less than exponential of A. I call this B. So y of n is less than B? Done. Done. No. Okay, implies that y of n is bounded. So S is stable. You got tricked
Yeah.
because you thought that you want the bound of the output to be the same as the bound of the input. We never said that. Nobody said that the output must have the same bound as the input. Nobody said that. It only, for stability, you only require that the output be bounded, but we don't impose any value on this bound. Because it's less than B. It's less than B. B is equal to exponential of A.
But then we can just say it for a lot of the examples. So what you can say is
No. It has to be a number. When we say there must exist a constant A has to be a number.
Okay, so
Infinity is not accepted as a number.
that means as long as it's a value, like it's an integer, we can call it exponential. So as long as we find an integer as
You want to find a number that is larger than your x of n everywhere. A number. Infinity is not a number. It's not. Because if you accept infinity as a number, then every sequence is bounded then.
E of A is like very close to
Exponential of A is always finite. Always finite. A is a number. A is a number. You see, as soon as you take a sequence that is bounded, there's a value of A. I'm not telling you how much, but there's a one value of A that corresponds to x of n. This A is a number. Exponential of A is going to be a number. You got tricked because you say, oh, exponential of A is much larger than A. We don't care about this. Stability never imposed anything about this. No, now I'm going to say that engineers, they don't like this type of stability because engineers, if it grows too much, they say, no, I don't accept. But here, we're not talking about engineering yet. In fact, we will never talk about engineering on stability. It's because it's too hard. I mean, you have to take electronics 2 or things like that to know about this.
So will you see examples where it's not stable?
Yes, but I think some people want to leave now. Looks like that. I mean, there will be 7 examples in total.
আমি আমার বাট আগে তোমারটা বলো তোমারটা আমার মনে হচ্ছে